Hello. Today we're going to cover more about how to solve differential equations using power series. But before we do that, we have a few vocabulary words to learn and some definitions and theorems and whatnot. So the first thing is we have to define what an ordinary point is and what a singular point is because the book uses them and it seems a bit like a mystery if you don't know what they are. So if we have a second order linear homogeneous differential equation and we put it into standard form, like we have here, then a point x equals x naught is said to be an ordinary point of the differential equation if both the coefficients p of x and q of x are analytic at x naught. Okay, that word analytic, we're going to have to define that in a moment. Okay, and actually, let me do it right now. For a function to be analytic at a point just means that it is defined at that point. Okay, so I want those to be very clear because these words are used almost before they're defined, and then it's really confusing about what we're talking about. So we're just saying that the coefficients p of x and q of x have to be defined at this point, and then it would be called an ordinary point. And when a function is defined at a point, we say it's analytic at that point. Okay, so an ordinary point is a point the function is defined at. An analytic function means that it's defined at the point as well. Okay, now a point is said to be, and let's just change the color for this, maybe we'll go with blue. A point that is not a point that is not an ordinary point is said to be a singular point of the differential equation. And so what this means is that the differential equation is not defined at the point. Right? So like if there's a fraction and there's a value of x that would make it so you divide by 0, then that's a singular point of the differential equation. Okay? All right. So I like to think of this as like talking just about the domain restrictions for p of x and q of x. And then, on the flip side, this just means that a singular point is a value that the function's not defined at. An ordinary point is a value that the function is defined at. That's it. All right, so we have another theorem. It's the existence of power series solutions. In the past, in 1.2 and 4.1, we talked about the existence of a solution. Now we're looking at the existence of a power series solution. So here it is. If x equals x naught is an ordinary point of a second order differential equation with linear constant coefficients, remember that just means that the differential equation is defined at the point. We can always find two linearly independent solutions in the form of a power series centered at x naught, that is, y equals the summation of c sub n times x minus x naught, all raised to the n power. And a power series solution converges at least on some interval defined by x minus x naught in absolute value is less than r, where r is the distance from x naught to the closest singular point. Okay, so r is the distance from x naught to the closest singular point. In other words, r is the distance between x naught and the nearest point that our differential equation is not defined at. Okay, so solution of this form is said to be a solution about the ordinary point x naught. Let's look at an example of this. Without solving this differential equation, we're going to find the minimum radius of convergence of the power series solutions about the ordinary point x equals 0, and then about the ordinary point x equals 1. So we need to put this into standard form first. So in standard form, we have y double prime plus x over x squared minus 7x plus 10 y prime minus 4y is equal to 0. So right away I could see here that I've got a fraction, and that fraction has a denominator and there are values of x that would make that denominator equal to 0. So we need to find the singular points. That is, the points that make this undefined. By solving x squared minus 7x plus 10 is equal to 0. Well, this factors. It factors to be x minus 5 times x minus 2 is 0. So x is 5 and x equals 2 are singular points of the differential equation. So they are the values of x for when the differential equation is not defined. Okay, so dE is not defined at these points. Okay, so they're asking us to find the minimum radius of convergence of the power series solution about the ordinary point x equals 0, and then about the ordinary point x equals 1. I'm just going to look at a simple little graph where I have 1, 2, 3, 4, 5, and so on. And I have singular points at 2 and 5, so I'm going to draw open circles around them because that tells me my differential equation is not defined there. Okay, so let's call this the first part. We'll call it the minimum radius of convergence about x equals 0. Well, if I look at x equals 0 on this number line, x equals 0 is right here at the origin. And let's real quick go back up here where it says r is the distance from x naught to the closest singular point. Well, the closest singular point is 2. Okay, so in that case, let me just do this. And I want to make a copy of that. Perfect. Okay, so for here, r is equal to 2. That's the minimum radius of convergence about x equals 0. Right at 2, we're going to have issues, and so we can't go more than 2 units away from the ordinary point x equals 0. If we look at the minimum radius of convergence, just do convergence about x equals 1, well then things are a little bit different. Let's go over here and grab this graph and move it over here. Okay, now we're looking at x equals 1, which is right here on the x-axis, and the distance between here and the nearest singular point is r equals 1, because it's just 1 unit away from 1 to 2. Okay, that's it. That's all we're doing. Not too difficult. Okay. We won't be doing this for all of our problems, but we'll know that we could do it if we had to determine what the radius of convergence is for our power series solutions that we find. In the meantime, let's go over that process for solving using series solutions one more time. We did this in the previous section for first order. The only difference now is we're at second order. So first, note that all of our problem solutions will be about the ordinary point x equals 0. Okay, so that means in the power series, we don't have x minus something, we just have x to the n. All right, so we're going to assume a solution and its derivatives. Y will be equal to the sum, n goes from 0 to infinity, of c sub n x to the n. Y prime is the derivative of that, and remember that the counter starts at n equals 1 now. And we just take the derivative of x to the n. So inside the series, we have n x to the n minus 1. Y double prime, we're going to lose another constant term, so n will start at 2. And we take a derivative of n x to the n minus 1 and get n times n minus 1 x to the n minus 2. We're going to substitute these series into the differential equation. Then we'll distribute anything that needs to get distributed. We'll adjust the indices in the sequence so that all powers of x are n. Then we will add out any terms in any of the series that need to be added out to ensure that all counters start at the same number. Once we've done that, we factor out the summation and rewrite so that we have a coefficient for x to the n that is in terms of the c sub n's. We'll equate coefficients using the method of undetermined series coefficients, similar to 4.4. And then we will substitute the coefficients back in to come up with the first 3 to 5 terms of each of the 2 power series solutions for each differential equation. This is a very long process. I'm going to do one problem and go over it in great detail. All of the problems follow the same process, okay? So if you can do one, you can do the others, all right? All right, we're supposed to find 2 power series solutions of the given differential equation about the ordinary point x is equal to 0. We have x plus 2 in quantity times y double prime plus xy prime minus y equals 0. So we are going to first substitute the series forms. Okay, we're going to sub the series forms of y, y prime, and y double prime into the differential equation. So we've got the x plus 2 on the outside times the sigma notation for y double prime, where n starts at 2. I'm not going to write the infinity at the top. It's like one less thing I have to write. We know these are infinite series. So I have the sum n starts at 2. We have c sub n, n times n minus 1, x to the n minus 2, plus x. And then for y prime, we have the sum, where n starts at 1, of c sub n, n, x to the n minus 1. And then we have minus y, which will be the sum, n starts at 0, of c sub n, x to the n, and this all sums up to 0. Okay. So right here, we're at step 4. We're going to distribute anything that needs to get distributed. So let's distribute. Now the distribution's a little bit strange, possibly. So if I look at this, the series itself needs to get distributed to the x and the 2, okay? And so I'm going to end up with a sum of 2 series from this first term that I've got here. So when I do this, I'm going to write the series when I first distribute it to the x, and so the x is going to come inside. Actually, you know what? I'll do it in small steps. We have x times the sum, n is 2, c sub n, n times n minus 1, x to the n minus 2, plus 2 times the sum, n is 2, c sub n, n times n minus 1, x to the n minus 2, plus the next term, that x, when it distributes into the series, it's going to multiply with the x to the n minus 1, and it'll simplify to just be, the power is going to be n. So we have n equals 1 of c sub n, n, x to the n. And then the last one needs no fixing for the power. We have the sum, n equals 0, c sub n, x to the n, and this all is equal to 0. Next, I'm going to distribute the x, and I'm going to distribute the 2 into the first 2 series. When the x distributes in, it will combine with the x to the n minus 2, and it'll leave us with the sum, n is 2. We have c sub n, n times n minus 1, x to the n minus 1 now, plus the sum, n is 2. The 2 just comes in. 2 c sub n, n times n minus 1, x to the n minus 2, plus the sum, n is 1. I said I'm not going to write the infinities. C sub n, n, x to the n, and then minus the sum, n starts at 0, c sub n, x to the n, and that's all equal to 0. Okay. Now I need to, what's my next step? Let's see, I've distributed. Number 5 says adjust any indices in the sequence so that all powers of x are n. Okay. So in the first series in here, it looks like x is raised to the n minus 1, which means I need to add plus 1 to all the n's in the sequence, but I have to counter that by subtracting 1 from the counter. In the second series, The x is raised to the n minus 2, which means I need to add 2 to everywhere there's an n in the series, and that means I subtract 2 from the counter. The third and fourth series both have x to the n power, so those are okay. We just need to fix the first two. So here we're going to shift the indices. So we have the sum, n starts at 1 now because we're subtracting 1 from the counter. And in the sequence, we add 1 wherever we see an n. So we get c sub n plus 1 times n plus 1 times n, x to the n. Plus, the second series, we subtract 2 from the counter, so now it starts at 0. And we add 2 everywhere in the sequence we see an n. So we get 2 c sub n plus 2 times n plus 2 times n plus 1, x to the n. And the last two, they're fine how they are. So we have plus the sum, n is 1, c sub n, x to the n, minus the sum, n is 0, c sub n, x to the n. Set that equal to 0. Okay. The next thing we have to do is, our powers are good, so we need to, in the second series, we need to add out n equals 0 term. And in the fourth series, we need to add out the n equals 0 term, because the other two series start at 1, okay? So when we figure out the n equals 0 terms, I'm going to write those first. So the n equals 0 term, I have 2c sub 0 plus 2 times 0 plus 2 times 0 plus 1, x to the 0. That's from the second series. From the fourth series, I get minus c naught x to the 0. Okay. Then, plus, here's what's going to happen. I have the sum, n is 1, c sub n plus 1 times n plus 1 times n, x to the n, plus the sum, n is 1 now, 2 c sub n plus 2 times n plus 2 times n plus 1, x to the n, plus the sum, n is 1, c sub n, x to the n, minus the sum, n is 1, c sub n, x to the n, and I'm running out of space, bring it up to the top and put my equals 0 in there. Okay, now what I'm seeing here is that I have a common sigma notation for all 4 series that I can factor out on the left, and I have a common x to the n variable that I can factor out to the right from all of the series. So when I rewrite this, I'm going to do a lot of simplification here. First, those two terms, I can rewrite those. I have a 2, I have a c sub 2, I have another 2, so it's 4 c sub 2, that's it from that first one, minus c naught. Okay, that's going to be my constant term, plus I'm going to factor out the sum, n is 1, and now I'll put in my infinity, and then I'm going to build some brackets, and I'm going to gather all those coefficient things that are in there. The x to the n I'll factor out onto the right. So inside the brackets I have c sub n plus 1 times n plus 1 times n. From the second series I have plus 2 c sub n plus 2 times n plus 2 times n plus 1. From the third series I have plus c sub n, and from the fourth series I have minus c sub n. Close the brackets, write x to the n, and this is all equal to 0. Okay. Now I have a polynomial on the left, and on the right I have 0. So I'm saying that, in order for us to solve for these coefficients, we need to say that each of the coefficients is equal to 0. That's how we would sum up a bunch of unlike terms and get back 0. And we need to pay very close attention to what each of the terms in here represents. So the 4c sub 2 minus c naught, this is the constant term. And it has to equal 0. So 4c2 minus c naught is 0. Those are like terms. They're both constants. Okay? from this, we can get that C2 is equal to 1/4 C naught. Okay. Now, our counter starts at n is equal to 1. Our powers of x will start when n is equal to 1. So the very first term we would get out of the sigma notation would be x, a linear term. And that makes sense because we already have a constant term, 4c2 minus c naught. It's taken care of. And so as the counter runs, we'll get the linear term, we'll get the square term, we'll get the cubic term, and so on and so forth. But in general, what we have here is that this c sub n plus 1 times n plus 1 times n plus 2c sub n plus 2 times n plus 2 times n plus 1 plus c sub n minus c sub n has to equal 0. So this is like where up here we're factoring out the summation and we rewrote it, and now we're getting ready to equate coefficients by saying that all the coefficients have to be equal to 0. Okay, so now we're going to actually do the equating. All right, so from the constant term, we got C2 is equal to 1/4 C naught. We got no information about C naught or C1. So I'm going to say C naught equals C naught and C1 equals C1. That's all I know about them right now. Okay. Now this general form right here, I'm noticing the biggest term is C sub n plus 2, and by biggest I don't mean it has the largest number value. I'm saying it is a later term, okay? C sub n comes before C sub n plus 1, and they both come before C sub n plus 2. You always take the bigger term and solve for it in terms of earlier terms, okay? So this means that I get 2c sub n plus 2 times n plus 2 times n plus 1, and I move everything else over. It's equal to c sub n minus c sub n minus c sub n plus 1 times n plus 1 times n. And then I can finally totally solve for c sub n plus 2 will be c sub n minus c sub n minus c sub n plus 1 times n plus 1 times n, all divided by 2 times n plus 2 times n plus 1. One thing I might do here, notice in the numerator I have that c sub n minus c sub n. I'm going to actually pull that out and write it as c sub n times 1 minus n. It'll just be a little bit less in my calculation going on there. Okay, it looks like we've got some information. We know C naught is just C naught. We know C1 is just C1. So that's stuff we know. Okay. We know C2 is 1/4 C naught. And then we've got to find more terms. So we're going to use this general form to get more coefficients. Okay. So the way I do it, I create a table. I've got my n value, and then I've got my c sub n plus 2. It's equal to c sub n times 1 minus n minus c sub n plus 1 times n plus 1 n over 2 times n plus 2 times n plus 1. Okay, I'm going to start at n equals 0. And then in my general form, I'm plugging in n equals 0 everywhere. So that means I'm finding C2. I already know C2 is 1/4 C naught, but what I'm going to do by finding this here is confirm that my math is actually right, that I didn't mess up somewhere. So I should be getting here that C2 is 1/4 C naught as well. So when I plug in n equals 0, I get C naught times 1 minus C1 times 0 over 2 times 2 times 1. This is equal to 1/4 C naught, which is what we had hoped for. Okay, next one. When n is 1, then I plug in 1 wherever there's an n, and I get C3 is C1 times 0 minus C2 times 2 times 1, all divided by 2 times 3 times 2. So the C1 times 0, that's going to go away. And then I get a negative 2 over 12, which is a 1/6 C2. But C2 is 1/4 C0, and I have to put that in there. My goal is not to have a whole bunch of unknowns. I want to get everything in terms of C0 or C1. Okay? So since C2 is written as 1/4 C0, I can substitute that in here. And then simplify to get negative 1 over 24 C0. Okay, n is 2. I'm going to get C4. And C4 is equal to, let's see, C sub 2 times a negative 1 minus C sub 3 times 3 times 2 all over 2 times 4 times 3. Okay. Now, what's going to happen here is I need to clean this up a bit because otherwise it's going to get super messy. The denominator is 24. So I have a negative 1 over 24 C2. And then I have a minus, that's going to be 6 over 24, which actually reduces to be 1/4 C3. Well, C2 and C3 are written in terms of C0, so I need to put that substitution in. So I have negative 1 over 24 times 1/4 C0, and I have minus 1/4 times negative 1 over 24 C0 for the C3. Those are the same numbers, but one's minus, one's positive. This adds up to 0. So there's no C4 term, which means there's no x to the 4th term. Okay. Now I have n is 3, so I can get C5. This is as far as I'm going to go to. C5, n is 3, we're going to get C3 times negative 2 minus C4 times 4 times 3 all over 2 times 5 times 4. C4 is 0, so that second piece is just going to go away. And this is going to simplify to be a negative 1 over 20 C3. And then I plug in what C3 is. I have a negative 1 over 20 times a negative 1 over 24 C0. And that's going to simplify to be 1 over 480 C0. And that's good. I've got 5 terms. Okay, so our solution, for the general solution, remember, this is all premised on what we let y be in the middle, in the beginning. Y of x is C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4th plus C5x to the 5th, and all the others, infinitely. Okay? Now, I didn't write this in sigma notation because it's not as clear when I write it in sigma notation that we're just trying to find the polynomial solution. When I write it this way, it's much more clear, like, oh, I see C0, I see C1x. I don't replace those with anything. I leave C0s and C1s. The C2 I've got to replace with a 1/4 C0, so let's do that. So we have C0 plus C1x plus C2 is 1/4 C0 x squared. Okay, and then C3 is minus 1 over 24 C0 x cubed. And then C4 is 0, so I don't have that term. So we have 0x to the 4th. And then C5 is plus 1 over 480 C0 x to the 5th, and so on and so forth. Okay, now I want you to notice that we have one C1 term, and we have everything else has a C0 in it. So I'm going to rewrite this by reorganizing things. This becomes a C1x plus a C0 times 1 plus 1/4 x squared minus 1 over 24 x cubed plus 1 over 480 x to the fifth plus the dot, dot, dot. It goes on forever. Okay, what I have here is a linear combination of two solutions. This is C1, Y1 plus C naught, Y2. I know the naught, that throws things off, but we'll stick with it, okay? So the two solutions are y1 of x is just equal to x, whereas y2 of x is equal to 1 plus 1/4 x squared minus 1 over 24 x cubed plus 1 over 480 x to the fifth plus the dot, dot, dot. And that's it. So in WebAssign, they are going to be asking these as multiple choice questions. Don't try to narrow down your choices. Just do the work. Because on a test, I'm not going to give multiple choices. The book doesn't give multiple choices. But I don't know why WebAssign does. However, you need to be able to come up from first principles of let y equal sigma notation c sub n x to the n, and walk through this whole process until you come up with your two solutions. Once you have them, look at your multiple choices and pick the one that matches. It should work, okay? As always, if you have any questions at all, please reach out.